Okay guys, here we are for lecture 7, which is the continuation of loads. We've covered most of them, the important ones, or certainly the ones that you're going to be thinking about the most. I'm going to mention a few other load types that you should definitely consider and definitely be aware of, and one that makes a fantastic math question. But the main focus that we're going to talk about in this lecture is how you combine those loads. So you can imagine, back when I was sitting on that table over there, there's the weight of the table, but there's also the weight of me on the table. But the table itself is a dead load, and Shannon is a live load. So how do we combine those and give them basically different importances, or different values, or different weight to them? Those are all such bad words because we use them in other places in the lecture. How do we assign different use importance factors? How do we assign, different tiering categories to them? How about that? The odds of the weight changing aren't that great because we wouldn't want to use more material. We know what material is usually available. But the weight of me could drastically change. I could go eat a cheeseburger. I could go have another baby and climb up there. So knowing the variability probability in your different loads has real value. And that's what we used to not do back in the day. We assigned all the loads the same kind of probability of variability. And now we've separated those out. So I have not made my mouse bigger for you guys. And of course, this is not on the right screen anymore, so let me just change my mouse settings for you so that you guys can see them a little bit easier. In the meantime, watch a lovely image of my child shortly after he was born. I think he was only like 3 weeks old there. So just mouse. Yeah, okay, that's the right mouse size for you guys now, okay. Okay. So you guys, what I did last term, because there was a group that did this class last term, I created an example project for part 1. Not part 2, because we're going to do a bunch of examples like that towards the end of the term, and you'll have examples. You just have to then go do the work. But part 1, I could understand, has a lot of ambiguity in it. The idea here is that it's not a building. Remember, so the loads might not be the same. You might not need building loads on these. You, as the architect, needs to stop and think about your object and think about what loads could be applied to it. And remember, for each kind of direction or type of load, you need to think about the worst case of all of those. So a half kilonewton person sitting in the middle of a couch versus a full kilonewton person sitting in the middle of the couch. Well, the full kilonewton person is the worst case load. So both of those aren't two different cases. Those are the same case, with the 1 kilonewton load being the worst case. You might have something very small. I've had people do a teacup, and there's no way you could actually, unless it was gold, and even then you couldn't do it, you could not get 225 pounds into a teacup. So that's not a realistic load on that. So I did one imagining a crib. Now, I did that example project in 20 minutes. I expect you to spend more than 20 minutes on this. And it's not because I was an engineer that I was able to do it in 20 minutes. It was because it's not that hard. So I expect you to think just a little bit more about your object. You could probably do a nicer drawing than me, I hope, but I'm not, there are some points for making it look good, but I'm not that obsessed about it. Try not to, unless you have the most beautiful handwriting, which that could be very a lovely effect. Don't scribble on a piece of paper. That doesn't make it easy for me to mark it and give you great marks. This happened one year. write it on the back of a cell phone bill and then take a picture of it with your cell phone where you can actually see the information from the cell phone on the back reading through. That was a very weird one. Obviously, they did not do very well on that. So try to just put a little bit of class into it, if you will. Part 2 is the one that is more heavy on the math. Part 1 is where you kind of get to explore being creative a little bit. This is probably a good place to talk as well about the fact that I know you guys are overwhelmed. I can't even imagine how crappy it is for you guys. Whether you are stuck with your huge family, whether you're also a parent. There are some students that have been parents throughout the years, and you're trying to deal with your own kids. Whether you are by yourself, I'm an extrovert, that would be horrible for me. I get it. This is really fracking crappy. The admin staff or at the university, they are losing their minds. They're exhausted and overwhelmed as well. The professors are exhausted and overwhelmed. And I fully understand that you guys are exhausted and overwhelmed. If you need time, if you need something, reach out. What I can't do is change deadlines for entire classes because that just ballparks the problem towards the end. I thought hard about saying, well, maybe the assignments are just available until the last day. Here's the due date, but I won't download the marks and I'll make them available as markable items until the end of term. But then I can't post the answer solutions, which really is what helps people study. So, it's I would love to do that for you, except then I can't post the answer sheets. So it's a thing that has me a little bit trapped and bound. But that said, I'm not a monster, and if there's something going on, or you need help, or something, you have to let me know, and between me and the TAs, we will do whatever we can. I know the TAs have done a lot for moving around time sessions and making them available. If you find that is impossible for you, you have to let them know. They will obviously do whatever they can, but what they have to do is make it the best solution for the majority of the class. Understanding that time zones make it very, very, very hard. The TAs are also bound by time zone constraints, and the majority of the class being within certain time zones. So if you are somebody outside of a time zone, you might have to schedule your own availability with the TAs to try to work something out for that. But they do have those set time slots to be available for you all. All of this to say is that we want to do whatever we can to help you, but we can't just give you all the answers. But we'll do whatever we can, is really what I'm saying. All right, first new load that we haven't talked about yet, and that's soil pressure. So soil, if you've ever been to the beach and you've dug a hole in the sand, and your pesky sibling has come and stood right on the edge of it. You had a perfect hole. It was perfect. It was miraculous. And your sibling comes along and stands on the edge, and the soil caves into the hole. That soil wants to be in that hole. It doesn't like to be bound up on the side. Now you can imagine if you did it in dry sand, it would be really hard to dig the hole. It all just comes in. If it's too wet, it all just comes into the hole. And you like this certain kind of stickiness to the sand. Well, all of these are things we have to worry about when we're doing our structural engineering. So what we do is we dig a hole carefully. Sometimes we might have to dig a bigger hole than we need, and then we put concrete in the ground, and then we might pile soil back up against it. We also like to tie the top of the concrete together to stop it from just tipping in. Obviously, we have retaining walls that don't have a floor there to brace it at the top. And that is something that we design to as well, which I showed you when we talked about different foundation types. So the things we have to think about when we're designing for soil, because you can imagine now, we need to design this concrete wall to resist all of this soil trying to push in this way. All of the soil wants to fill in our basement. let me get my pen working here. So all of this soil wants to push in that way. And we want to make it not do that. And so we build this concrete wall to resist it. So there's two parts to it. As we get deeper down, you guys have seen from probably building in the sand that the soil tries to fill in the bottom first. That's because that's where the pressure is the highest. As we go down the soil, we have more weight above, and it's the weight above that's trying to make it fill in that hole. So at the very top, there's no soil above it, and it's not trying to go in the hole. Down just a little bit, there's the weight of the soil above, and we're trying to push in some fraction of that weight. As we go all the way down to the bottom of the foundation, we have all the soil up above, which means we're trying to push in to our hole with some fraction or some percentage of that weight. And then, just like your pesky brother or sister, if we have a live load, or what we call a surcharge, on the soil right by that hole, it's adding to the weight that's trying to push into the hole. So you guys remember back when we talked about live loads? Why would you care so much about vehicles on sidewalks? Well, if this is a vehicle accessible spot right here, like a laneway, we would have, instead of 4.8 live load for a person, we would have a very poorly drawn fire truck adjacent to that, causing a surcharge of 12 kPa. So our soil equation for the pressure at any point down the height of this wall, so the pressure due to soil and groundwater and any weights above, is K times Q plus K times gamma times H. Well, K is something that comes from the geotechnical engineer. I like to think of it almost as a sticky factor. How bound is our soil together? And that is given to us by the geotechnical engineer, and it ranges from 0.25 to 0.5. Q is the surcharge, or that person or vehicle load that we would have here on the soil outside. Gamma is the weight of the soil. You can imagine heavier soil wants to push into the hole more. So that again would come from a geotechnical engineer, but it's usually somewhere around 20 kilonewtons per meter cubed. And H is the depth below grade. So as you go further down, you have more and more weight above trying to push that into the hole. So let's do an example here. And I'm trying to just remember if I was going to do it aiming down. Yeah, I'll probably do it aiming down for you guys. So the building previously discussed, I don't know what building, from last lecture, has a 2-story deep basement, each one being 4 meters deep. There's a laneway adjacent to the building that could be used for fire truck access. So that means we have to think about our surcharge being 12 kPa. The geotechnical report states that the weight of the soil is 19 kilonewtons per meter cubed, and K is 0.3. What is the soil pressure in kPa at the top and at the base of the foundation wall? Now this is a pretty easy calculation. I might just do it right on the screen here. You'll see me up close and personal as I lean forward, which means I'm very close to the camera. But it allows me to just keep recording and not having to stop and go back. So they've said we have two floors of basement that are 4 meters deep each. We know what the surcharge is. If it is got a vehicle access. That means it's got to be 12 kPa. They've given us the weight of soil, and they've given us what the K is. We want to know what P is at the top and what P is at the bottom. So we want to know at a height of 0, or at a depth of 0, and at a depth of 8 meters. So if you guys remember, P equals KQ plus K gamma H. I'm just going to change this to a white pen. So P, pressure, equals K, which is the coefficient friction of the soil. Q is the surcharge. K is, again, that same number from the geotechnical report. Gamma is the weight of the soil, and H is the height. And we wanted to know the pressure when we were at the top, and we wanted to know the pressure when we were 8 meters down. So K, they told us in the question that it was 0.3. Are you bird? All right. So P equals 0.3 times our surcharge of 12 kPa plus 0.3 times our soil weight of 19 times our height of 0. So let's plug that into our calculator. We've got 0.3 times 12 plus 0.3 times 19 times 0. We've got 3.6 kPa of pressure pushing on the wall at the top of the wall. So now we want to know what that pressure is 8 meters down. Everything stays the same except for the height. So we've got 0.3, which is our coefficient for the soil, times 12, which is our surcharge, plus 0.3 times 19 times 8. And at the bottom of the wall, our pressure is 49.2 kPa. If you guys remember, Arnold over a 1 meter by 1 meter squared was 1 kPa. That's like pushing at the bottom of the wall with the weight of 49 Arnolds. That's a lot of Arnolds pushing in at the base of that wall. So here's just the pressure distribution of that wall. At the top of the wall, the soil's trying to push in with a pressure of 3.6 kPa, and down at the bottom, it's pushing in with 49.2 kPa. So you can see, as we go pretty deep into the ground, soil is a massive load, which is why concrete makes such a good construction element for foundations. We have it everywhere, and you throw a little rebar in and you can have the same strength everywhere. Versus our steel construction, for example. Where locally, where we would have beams, or in this case, rakers, to make a foundation wall, we would have very good ability to resist the soil. But in between whatever we had there would be somewhat weak, like our metal deck, if we were talking about something on plan. So that's why concrete, as much as there are problems environmentally with concrete, it can be the most efficient material. To do something else in a foundation environment like that, we would end up needing so much more material that that cost payoff of which one is the least environmentally hazardous might change. Funny that I keep losing the blank page ones. Anyway, here's that worked out, again, a little bit cleaner, so you can see it. You still have access to it, even though that page of calculations disappeared. We have it right here for you. Clearly, I have it again worked out for you. I have it multiple times worked out for you. All right, so another load case that we have to worry about, although, to be honest, not very often. It depends. You might go into a very particular field of architecture, and it might be a very important load case for you again and again and again. In my career, the check for temperature change on my structure has only been a handful of times. So you can imagine that, you guys all probably remember that steel as a metal, and I'm using steel because it's the most drastic. All of the materials are affected by this, but steel the most so. If it gets cold, it contracts, and if it gets hot, it expands. So I have two anecdotal stories here for you. There was a project where there was concrete piles, and they had a steel girder sitting on top of it. And they put it in, they just loosely set it there. It was safe, it couldn't fall over. It was just sitting where it was supposed to be, but it was the end of the day and they didn't have time to put the anchors in. So everyone went home, no big deal. It was like a fall day, or it was a sunny, warm day, and then it got very cold overnight, and the steel contracted, and it all of a sudden didn't fit on the, it wasn't long enough to span to the piers that it was supposed to be on, and it contracted and fell down. Now, it was overnight on a construction site, and no one was there. Luckily, no one was injured. Another story, there was a project that I wasn't working on, but was some story I had heard from someone, where they had installed all the steel, they did their survey, they were very happy with the steel location, and the window guys came in, and they're like, "You're crazy, we can't install these windows, nothing is where it's supposed to be, like, this is ridiculous," and they walked off the site. So they brought the steel guys in, and surveyors, and they measured everything, and everything was perfect, it was all where it was supposed to be. The window guys came back that day and were like, no way, it's all still so off, we cannot install these windows. So what was happening was, it was fall, and you guys know that, especially here in southern Ontario, you can get long shadows and cold nights. So the site was in shadow, and it had been a cold night, so it was like -5 in the morning, and then the sun came out, the shadow moved off the building, and it turned into like a 25-degree day. And so the steel all swelled or expanded somewhat, and so the windows didn't fit. What they did is they just accounted for that, and they were able to deal with it. Now here's why it's usually not such a big deal. You put the building in an envelope, and you don't have this problem anymore. It's usually a construction tolerance issue, even on the projects I've been working on. Where it might be a problem is if you have a community center where you have an ice rink and a swimming pool in adjacent portions of the building. You could imagine you want your ice rink to be down around, 4 degrees, and you want your swimming pool side to be up over 30 degrees. So that's where you can start to see some of these temperature effects, even inside the building. But even those are not the common issue. It's good to know they can exist, and it's good to know that you need to check it. But it's not always a thing you need to check. What you have to do is be analytic about it and say, do I need to do this check? And often the answer is no. Pre-stress is another one. So you can imagine that if I try to compress this elastic, it doesn't work. What happens though if, gotta be careful with my messed up finger. What happens if I put a bunch of weight at the end of this elastic? So now I've got some weight on this. Well, now this has been stretched. There's a force tensioning it some, or pre-stress on it. I can now start to push up, and what you guys can't tell is that when I do this, there is a brief amount of time where my elastic doesn't go slack. That as I push up, there's a small amount where what I'm doing is unloading it, the weight of the pens that I put on it. So that is pre-stress, and that's what happens when, for example, we use a saw like this. You guys know that if you don't stretch this handle up to pull that saw blade taut, if you try to push on it, you're going to bow your blade. But what we do is we stretch it to an amount that it is compensated for the fact that we're going to try to push against that very fine, thin blade. It's what we do for cables in structures. We pre-stress them so that we have some sort of tensile capacity built into them. Or some sort of pre-stress in them that allows them to not just be floppy. Children slamming against doors. Another one that we definitely think about, but it's not often the governing design case, until it is, and then we have to be really smart about it, is vibration. Now, I talked in the very first lecture loosely about vibration, that we have continuous vibrations that can be steady, repeating loads like dancing or music, and they're often at, especially if it's a person-induced vibration, at 2.5 hertz. So we need to worry about that vibration. And we have equations that we look at. Most of the time it's not a concern. Times that it might be a concern are lightweight structures, which sounds kind of weird, but that's because they don't have the mass to kind of resist the load, or they're very sensitive to vibration. Feature stairs, very susceptible to vibration. Footbridges, very susceptible to vibration. But we also have human ability to cope with it. On a footbridge, you kind of get that there will be some vibration. On a feature stair in a very fancy building, you don't want to feel it move at all. So your tolerance for vibration changes depending on your location. And we have to, as engineers, appreciate that. And so there are varying criteria depending on things exactly like that. There is damping, where you might do a heel drop. I wonder if I can, you guys could see my camera respond to what I would call, what would normally be a heel drop kind of load test or vibration test. So watch how it moves a lot very quickly, and then it moves less and less and less until it stops moving. So the reason it stops moving so much so quickly is the mass of the table basically damping that vibration load. I show you guys, or I made available to you, a video for amplification of vibration. And that's when two different things, or when the object has the natural frequency that is the same as the applied repetitive load. So if they both have the same frequency, you can get amplification. And that can have disastrous results. It can be due to human movement, wind, or seismic loads. Way beyond the scope of this course. If you guys ever join in my elective that I do, I think it's third year. I don't know. I don't know when they place me for it. But we do a whole lecture based on vibration design for elements to look at what you do and what it means. So those are all the loads I wanted to talk about. So now let's start talking about our strength design. So this is really the thing we care about. We do not want loss of life. Strength is about loss of life. We do not want lives to be lost because of our structures. So what we say is that we know the capacity of something and we know the loads on it. And that's what we just spent some time figuring out a little bit. We're going to have to take that a bit further. But we know that just making it strong enough to resist those loads might not be enough. That maybe what we need to do is make it increase those loads a little bit. And what we used to do is just apply the same increase to all the loads blindly and forget about what material it was and not touch that side of the equation. And we would say the capacity had to be greater than some amount of factor of the loads on the system. So we'd sum up all the loads and apply a factor. But we realized that that doesn't take into account the variability of the load type and the variability of the material. So what we do now is we increase the loads on the system, and we vary that depending on what the load is. And we decrease the capacity, and we vary that depending on what the material is. So we factor the load, and we reduce the capacity, and we make sure that factored load is less than the reduced capacity. We like symbols, so we'll use this symbol for load factors, and we'll use this symbol for load reduction factors. I know, we like to reuse our words, and it's a total pain. But if you see this, we're talking about reducing the capacity. And if you see this, it often means we're factoring up the load. We don't write this too often, because I'm going to show you what those load factors are right now. Sorry, you're good? Okay.
Yeah.
All right, we fight for...
Godspeed.
We fight for this space for phone conference calls and recording time because the other person has to go up into the nursery and it's cold and dark. It's not a nursery anymore, my kids aren't in there anymore. And so all of the stuff that made it warm and inviting is gone. So it's basically just a white box of a room with a chair. So I needed to make sure he didn't need this. So we're going to factor up the load and reduce the capacity and make sure that factored load is still less than that reduced capacity. Now, we like to know if we've done or not. You can imagine you factor the loads and then you forget, did I factor those loads or not? And you can't really remember. Well, the way we remind ourselves that we've done that is we write a little F right here. So if we're talking about axial loads and you see an F, well, that's a factored axial load. If we're talking about shear, and V means shear, we're going to touch on that in a couple weeks. If you see an F, it's the factored shear. M is moment, small f, it's a factored moment. Tension, compression. Same thing over here. If you see this small r beside it, that means we've reduced the capacity. And that's just to let us know that we have, in fact, applied those load factors and that reduction factor. Because sometimes we'll do a bunch of work before we apply the factors, and then very close to the end, apply them. And so this lets us know throughout the process where we are and if we have, in fact, applied those factors. This is called limit state design, or ultimate limit states design. This is the majority of the world now uses this method. Canada definitely uses this method. It is, the last holdout was soil design. When I started, we did not use limit states design for soil design. And then in, was it 2005, 2006, they applied limit state design to soil? Maybe even a little bit later. So not that long ago, it was the last holdout. They had to rewrite all the codes, rewrite all the methods, but everything now in Canada has to meet that limit state design. You still see some holdouts for products in the States where it might talk about the factor of safety method, but we know how to manipulate that into limit state design for ourselves. So there are two components within limit states design, or ultimate limit states design kind of heading. If we're talking about strength, which is what we're going to focus on for a good portion of the rest of this term going forward, is strength design, ultimate limit states. Now, the reason I want to show you these names is ULS often means ultimate limit state design. That means we're talking about strength. So if we are using importance factors, which we're going to talk about in a minute, no, we talked about importance factors already. Importance factors for strength design, we would often reference our ULS. If we were talking about importance factors for serviceability, remember wind and snow had different importance factors, values for serviceability cases. Well, that's when it's important to know if we're talking about our SLS, or our serviceability limit states. These both fall under the heading of limit state design. Ultimate limit states, or our load combinations. So this is where we start to combine those loads together. So our ultimate limit states for strength design have these combinations of load cases. So what they've done is they've said, you can imagine that you could have any of the loads all by themselves. It would be hard to have live all by itself because you'd always have your dead load there. So you could have dead load all by yourself. You could have dead load with a live load. You could have dead load with snow, dead with wind, dead with seismic. But what if your live load happens during the snowfall? Well, you could have dead and live and snow. But does it make sense that you would have the biggest jam-packed capacity in the entirety of your building at the exact same time that you would have your 1 in 50 snowfall event? And they take a look at the statistical probability of that and vary the load combination factors accordingly. And they've broken it down into the principal load, which is dead, plus one of those loads we've talked about. Live, snow, wind, seismic. And then they've said, whatever other load that we add on is the companion load. We don't often do multiple companion loads at once, and often they have different values. So if we had dead and live, we could have snow or we could have wind. If we had dead and snow, we could have as a companion load live or wind. If we had dead and wind, we could have as a companion load live or snow. And that's what this chart here shows us. If we have dead load all by itself, we multiply that dead load by 1.4. If we have a dead load and a live load, we multiply the dead load by 1.25 and the live load by 1.5. And then we stop and think, is there a possibility that we could have snow? If so, we also include 1 times snow. Is there a possibility of wind on that element? If so, 0.4 times the wind as the companion load. Now, this always throws people off. See this 0.9 dead load here? What happens if our dead load actually helps us out? So you're thinking, how could our dead load help us out for assuming our worst case loading? What if we had this elastic band and we were worried about it squishing like this? So say my wind was going to blow upwards on this. So my pens are my dead load. If we multiplied this by 1.25 and then thought about the wind load acting upward, it assumes I've got extra dead load that I might not have. What if these pens aren't as heavy as I thought, but I've got a load counteracting them? Well, in that case, I'd want to assume that I had less pen weight than I thought I possibly had, or 0.9. Now, I can tell you, you're not going to do many examples where the dead load could possibly help your strength calculation. Remember, we want the worst case load we can possibly work out of these. I will try to be very explicit when that appears. But when it often can happen is if we have a reversing wind load or a reversing seismic load. Most of the time, our things are all acting in the same direction. So we could have dead load all by itself, dead plus live plus snow, dead plus live plus wind. Dead plus snow plus live, dead plus snow plus wind. Dead plus wind plus live, dead plus wind plus snow. We're starting to get a lot of load combinations there. And then seismic, we don't multiply it up for anything here. We have dead plus our seismic, and then we could have 0.5 live plus 0.25 snow. Now, all of these, though, there's a possibility that these actually improve our load case. Again, not very often, but we would have to think about that too. So, here we have them. I like a handy little naming system so that I don't lose track of what I've done and what I'm looking at. So the U tells me I'm talking about an ultimate limit states load combination. And really, guys, this is about just good bookkeeping and good accounting. It's going to seem overwhelming, but often making a spreadsheet can help you out. So we could have a factored dead load, so 1.4 times our dead load. We could have our dead and live by itself, or our 1.25 dead plus live. Our dead and snow by itself, so 1.25 dead plus 1.5 snow. We could have dead and wind by itself, 1.25 dead plus 1.4 wind. We could then start to add in our companion loads, where we have dead plus live plus snow as a companion. So dead, live, snow as a companion. Dead, live, and wind as a companion. Dead, live, wind as a companion. And then we go through the same thing with snow, and then we go through the same thing with wind. But then we have that condition where wind might have been, the dead load for the wind might have been actually helping us out. Maybe if the wind is trying to lift up, and our dead load is going to decrease that possibility that we have uplift, we have to worry about an uplift possibility, or our lowered dead load, where we don't have as much dead load as we thought, and an increased wind load. Another good example to think of this, imagine an umbrella. You're at a pub or a restaurant sitting on the outside patio because it's COVID, and you know those umbrellas often screw in to a weighted base. And even on a windy day, those things can move around a little bit. Well, the wind load is trying to pull the umbrella up, and those blocks or that weight at the bottom is trying to hold it down. If we multiplied that dead load by 1.25, we're saying we have more dead load than we thought. And what we're worried about is this umbrella blowing away. So we want to be conservative and say, there's a possibility there's not as much dead load there as we thought. So let's assume it could be less than we thought, and then factor the wind load pulling it up, so that we're comparing those two things. And then we have our earthquake loads. Well, that's how many load cases? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 13 cases. These came directly from me writing out individually the cases from this table. But wind and earthquake need to be analyzed in each direction of the principal axes. So you guys remember we had our building, wind could blow in that direction, and it could blow in that direction, but it could also blow in that direction, and it could blow in that direction. So that's 4 directions of principal axes of wind, and 4 directions for principal axes of earthquake. So everywhere we had a wind case or an earthquake case, we need 4 of them. So we have our dead load plus 1.4 times our wind in the x positive direction, our x negative direction. Wind y positive and in wind y negative. That's a lot of equations all of a sudden. And do you guys remember in our wind load, we had that end zone? And I said that end zone was all about, if this is the roof of the building that I'm holding up for you guys, that's all about it wanting to make the building twist. So we had to we would have analyzed it with the end zone here, and then we would do another analysis with the end zone here. That means in this direction, we do the end zone here, the end zone here, 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 and here. Seismic has the same thing. So now all of a sudden, anywhere we had a wind zone, we need eccentricity at each end. So that would actually double all of those combinations. So that's even more. I don't think I listed that out for you. Snow and wind, we can actually go to a wind tunnel study, and they will give you broken down patterns of what the wind could be. When I did the Canadian Peace Bridge Plaza building at the border crossing with that kind of curved fancy roof, we had how many different snow load cases, but there was different patterns of the snow load that we could have fall on it. My model that I built, and there was different wind patterns and then the combinations of wind and snow amongst each other. The model that I built had 1,200 load combinations because we don't know which one's going to be the worst case. And it's not going to be the same worst case for every element in the building. So you can't just say, oh great, here's my worst case, I'm going to design with that. For each element within the building, you have to think about its own individual worst case load combination. So you can imagine tracking this data becomes a huge thing. It becomes a huge part of managing your information. You're not going to have to calculate 1,200 load combinations. You're not even going to have to calculate 40 load combinations. I will be keeping it pretty simple for you. I would keep it to most of the time dead, live, and snow. Even as we get further in, it's usually only dead and live or dead and snow. There are, because this is the lecture for talking about load combinations, we will look at some examples where there's dead, live, snow, wind, and earthquake. So 5 different load cases. But we're not going to worry about positive and negative and end zones and anything like that. So it would be just those 5 values and the load combinations. Almost just like this chart right here. It's almost like I gave that to you already. And you can see that earthquake has 2 different combinations, because if the earthquake load is lifting up, we use dead load to keep it down, but we wouldn't want to assume that live and snow are helping to keep it down. So those were our strength cases. Now you guys remember when I told you about serviceability limits. We looked at what the deflection limits were for different materials of different lengths in different usages. And I told you that there's not much you're going to be able to do with that until Lecture 4 of Structures 2. And that there would be more information I'd give you that you have to track, even though you still can't do anything with it. Well, that's our serviceability limit states combinations. This is all about deflection. So these would also then use an importance factor for serviceability. Remember, our snow and our wind had different importance factor values for serviceability than it did for strength. So we would want to track those things. So you can see here for a roof, we would have a serviceability load combination for dead and snow of 1 times dead plus 1 times snow. But it's not the same snow load we used in our strength design. Remember, the importance factor changes to 0.9 for serviceability of snow. Floors, for live, we would have dead and live, or live all by itself. And remember, we had serviceability deflection limits of dead and live, or live by itself, or dead and snow, or snow by itself. So eventually, in Lecture 4 next term, we'll start to compare these values to see what the actual deflection is and compare them to that allowable deflection we calculated at the beginning of this term. So let's do some examples now. I think everything else is an example. So I'll flip into shooting down mode and we'll touch on those examples now. All right. right, so the question they've given us is, what is the factored compression and tension loads on a column that could see a dead load of 12 kilonewtons in compression, 10 kilonewtons of live load in compression, 5 kilonewtons of snow load in compression, and then wind load could be up or down. So you guys can imagine in a braced frame that as the building blows back and forth, whatever our brace is could actually try to lift up a column or push down on a column. And that'll start to be more clear when we do some analysis later on in the term. So let's start with everything we know. So this is a ULS load combination activity. So we were given a dead load of 12 kilonewtons acting downward, live of 10 kilonewtons acting downwards, snow of 5 kilonewtons acting downwards, and then wind is 10 kilonewtons, but they said it could go down or up, so we have to worry about both of those things. We're going to learn about free body diagrams going forward in a few weeks, but you can imagine we're talking about a column that is standing there, and there is something at the floor stopping it from falling down into the floor, and something stopping the bottom of it from kicking out as if it was a ladder, and something stopping it from falling over here. And we're saying that we could have 12 kilonewtons of dead, 10 kilonewtons of live, 5 kilonewtons of snow, and then up or down we could have 10 kilonewtons of wind. Now we're going to work on free body diagrams. This was just for those of you who are visual. Sometimes it's helpful just to imagine what's going on. So we have a column that's being held in place here and loads pushing down, except for wind, which could push down or pull up. And we need to worry about our load combinations. Well, we know that the very first one is our dead load case, which is 1.4 times 12 kilonewtons, or 1.4 times 12. 1.4 times 12 gives us 16.8 kilonewtons. Great, so that is one possibility our column could see. Remember, these things don't all necessarily happen at the same time. These are all the possibilities that it could have. These are the maximum loads for each of these things we've calculated. Remember, dead load we know comes from whatever makes up the building and the tributary area. We know live load comes from an assigned value in the code and its tributary area. But it might not all always have that live load on it at the same time. We know snow comes from climatic data, and it covers an area of the roof or a canopy, but it might not be there. And then wind load, we don't quite understand how columns work with a wind load yet, but you can trust me that it very much can act as compression or tension in a column. And we know it comes from climatic data, and it has to do with it blowing on the building. There's also the option of roof suction. And we need to figure out the different possible combinations of all of these loads. So we know that there can be dead and the principal companion, or the principal loads. So we could have dead and live, or dead and snow, or dead and wind acting downwards. And for that, we knew that it could be 1.25 times our dead load plus our 1.5 times our live load. 1.25, it's 1.25 for all of these, times our dead load, plus the different factors depending on what principal load it is. Live and snow both have the same principal load factor. Snow could see 5 kilonewtons, and then wind is 1.4, and it was also 10 kilonewtons. So we can calculate all of these. So we've got 1.25 times our 12 kilonewtons plus 1.5 times our 10 kilonewtons of live, or 30 kilonewtons. It could have been 1.5 times 5 kilonewtons of snow, or 22.5 kilonewtons. And then there was the possibility that it could be dead plus 1.4 times 10 kilonewtons of wind, or 29 kilonewtons. So it looks like so far the worst possible combination of loads our column could see is 30 kilonewtons. But we know there are a few more conditions on these load combinations. These are dead plus the principal loads, but there could be dead plus principal loads plus companion loads. So we have a few more that we need to calculate. We can have, let's focus on live as the principal. With live as the principal, we could have snow as the companion, or we could have wind as the companion. So 1.25 times our 12 kilonewtons of dead load, and that doesn't change for either of those, plus, so live is still our 1.5 times 10, and our snow load is a companion load in this situation. So 1 times our snow load, which was 5 kilonewtons, or 0.4 times our wind load, which was also 10 kilonewtons. So we can calculate our load combinations for principal live load with its companion loads. 1.25 times 12 plus 1.5 times 10 plus 1 times 5 gives us 35 kilonewtons, or it could be 0.4 times 10, 34 kilonewtons. So it looks like that's our new contender for the worst case load this column could possibly see. But we have to think about the other load cases as the principal load case. So ultimate limit states dead with snow as the principal load and live as a companion, or with wind as a companion. So 1.25 times 12 plus 1.5 times our snow load was 5 kilonewtons, plus now live is our companion load, and live we had 10 kilonewtons. Ultimate limit states and dead, so 1.25 times 12 kilonewtons. Snow as our principal load, or 1.5 times 5 kilonewtons. And then wind as our companion load, which is 0.4 times 10. We can calculate these. 1.25 times 12 plus 1.5 times 5 plus 1 times 10, 32.5 kilonewtons, or 0.4 times 10 is 26.5 kilonewtons. Now we still have the possibility of wind being our principal load. So ultimate limit states, dead load, wind is our principal load, and live as a companion. Or ultimate limit states, dead load with wind as the principal load and snow as the companion load. So 1.25 times 12 plus, now wind is our principal load, so 1.4 times 10 plus 0.5 times our live load. And it's the same for those first two steps here. Or 0.5 times our snow load. 1.25 times 12 plus 1.4 times 10 plus 0.5 times 10 equals 34 kilonewtons, or 0.5 times 5, or 31.5 kilonewtons. Now, if you guys remember, we still had the possibility that wind is acting upwards. So not pushing down, but trying to pull up. And we're concerned about two things. We're concerned about this column compressing too much, but we're also worried about it pulling out too much, or stretching too much, or too much tension on it. So if we're worried about too much compression, these were all the cases where everything was acting down. Well, it looks like the worst case load here was this one for compression, or it trying to push in this direction. But if wind was acting upwards, we'd want to make sure that we didn't guess there was too much dead load on it. So we'd probably want to use the 0.9 load factor for dead, and we certainly wouldn't want to assume that there was live or snow there. Remember, if we're worried that this could pull up out of the ground or stretch too much, we wouldn't want to make the assumption that live or snow were there, because those would be helping us out. So we also have to worry about our ultimate limit states uplift condition, where we have dead and wind. So this one is 0.9 times our dead load plus our wind load Now here's the thing though. My compression load is acting downward and my wind load is acting upwards. So you might want to say that this is a minus 10. Let's even just rewrite that so it's a little bit more obvious for you. I kind of compressed it there a little bit. Times a negative 10, or the 10 is trying to go upwards. It's going in the different direction from all the other load cases we've looked at. So 0.9 times 12 plus 1.4 times negative 10, we get minus 3.2 kilonewtons. So it looks like there is a chance that this could have load going in the other direction. So we have to design for all of these load cases. We need to make sure all of these are less than our reduced capacity. And next term, we're going to figure out how to calculate the reduced compression capacity and the reduced tension capacity. Well, if all of these are in compression, you might as well only worry about the worst case one. And if these are the tension values, you might as well only worry about the worst case one. So we care about our worst case compression and our worst case tension. And we will need to make sure that those factored values are less than the reduced capacity. Or we need to make sure that CF equals 35 kilonewtons is less than CR. We don't know how to calculate CR yet. That's going to be our job next term. And we need our factored tensile load. Now, I'm writing T here. That means I know it's going in the other direction. Needs to be less than our reduced capacity for tension. And we will figure out how to do those calculations next term. And we need both of these things to be true to make sure this column is strong enough. So that was our first load combination example. We have another one. So you can see all of that worked out here. Let's go back and look at this building we were talking about last week, where we have our 4 bays at 8 meters and our 6 bays of 7 meters, I believe. And here's our plan that we had. And here was our elevation and our datums from both sides. So this is all stuff we looked at last week. And we calculated the dead load, and we calculated the live loads, and we calculated the wind load on all the sides of the building, and we calculated the seismic load in each direction of the building. Well, now we want to determine the ultimate limit states and serviceability limit states loads on the roof in KPA using the dead and snow loads we calculated last week. We want to determine the ultimate limit states and serviceability limit states loads on level 2, level 3, and level 4 in KPA using the dead and live loads we calculated last week. We want to know what the total load on the columns C1 and C3 are. Now, this one I don't think I'm going to work out step by step for you, mostly because I have uploaded an Excel file for you where I work through it step by step. You can look at the cell references and you can see step by step what's been done in that file. So I've provided it here. Well, actually, you know what? Let's do the first part. Let's do the first part together right now. And we'll look at the beginning steps of it together. I think that's not a bad thing to do here. All right, so the first thing they've asked us to do is determine, so step 1, let me make this bigger for you. So we want to determine the ULS and SLS on the roof. Now, last week, we calculated that the roof had a dead load of 1.32 kPa. We looked at the roofing assembly and we calculated that ourselves. We looked at the snow load climatic data and calculated that our building had a snow load of 1.12 kPa for ULS values, or strength values. We also know that if we are talking about serviceability criteria, that importance factor isn't 1, it's 0.9. And we calculated that we had a serviceability snow load case of 1.01 kPa. Essentially, it's our snow load times 0.9. And we want to know our different load combinations for our roof. Well, we could have dead all by itself, or 1.25 times 1.32 kPa. I'm going to write them all out and then pick up my calculator. Or we could have dead and snow, or 1.25, 1.4. You guys were all yelling it at me, right? 1.4 times 1.32 for our dead all by itself. And for dead and snow, 1.25 times 1.32 plus 1.5 times 1.12. That's it. There's no live up there. We haven't said anything about wind or seismic load acting as a gravity load on our roof. We only have 2 load combinations that we're worried about here at this point. So we can calculate 1.4 times 1.32 is 1.85 kPa, and 1.25 times 1.32 plus 1.5 times 1.12, we get 3.33 kPa. The worst case load is our 1.33 kPa. The second thing they asked us was to figure out the ULS and the SLS on level 2, level 3, and I believe it was level 4 is how many levels that we had in this building. Well, I forgot something. I haven't figured out the serviceability load cases that I need. So still finishing step 1, this was our ultimate limit states worst case load. So our ultimate limit states load is 3.33 kPa. But they also asked for a serviceability limit states case. But this one, we are not looking for the worst case. We have to track both load cases. This is super important. You will get marks for this accordingly. You need to track both. You will need to do it in part 2 of your project. You will need to do it on exam questions. I will be very explicit and give you the opportunity to write it in accordingly, but you need to be tracking both. Strength, we're worried about the worst case. Stiffness or serviceability, we're comparing them to different things. It will become more clear next term when we have that thing to compare them against. But right now, you have to trust me that we have to track both. We are tracking serviceability dead in snow and serviceability snow all by itself. And that was 1 times 1.32 plus 1 times 1.01. And this is just 1 times 1.01. 1.32 plus 1.01, we have 2.33 kPa and 1.01 kPa. This isn't a matter of finding the worst case one. 2, ultimate limit states and serviceability limit states on level 2, level 3, and level 4, I believe, are how many loads we have on this, or floors we have on this. And last week, we calculated the dead loads as 2.85 kPa. We looked at what the flooring assembly was, and we broke it down item by item and looked up what the weight of all of those items were and determined that the appropriate design dead load for these floors is 2.85 kPa. We were also told that it was an office building, and we looked up that live load for an office building is 2.4 kPa. So we need to figure out what our worst case ultimate limit states load case is, or our ultimate limit states dead, or our ultimate limit states dead plus live. We could add snow here, but it would be 1 times 0. So we don't really need to write that down. This is where getting good at it, you get to eliminate some things. If we had dead and snow, or if we had live on our roof, we would have more combinations we needed to look at. So 1.4 times 2.85, or 1.25 times 2.85 plus 1.5 times 2.4. So 1.4 times 2.85 is 3.99 kPa, and 1.25 times 2.85 plus 1.5 times 2.4 is 7.16 kPa. So we're saying that for every 1 meter by 1 meter square of floor, we're going to design it as if it was supporting 7.16 Arnolds. That's the weight we're designing that we would design this floor to. We also have to worry about our serviceability dead and live together, and serviceability live all by itself. Well, serviceability live all by itself is 2.4 kPa, and serviceability dead plus live is going to be 2.85 plus 2.4. So 2.85 plus 2.4 is 5.25 kPa. We don't pick the worst of these. We need to track both of our serviceability cases, but we do need to look at what the worst ultimate limit states load combination is, and it is 7.16 kPa. Now that would be for those individual floors. The next thing they asked us to do was to think about the columns that we would be designing, that we would design. The very first column they asked us to look at, so here you can see all of these values worked out that I just did over here in the corner. They asked us to design column C1. So we have column C1 is right here, and it is picking up a quarter of this bay and a quarter of this bay, or half of 7 meters in this direction, half of 7 meters in this direction, making 7 meters on this side, and half of 8 meters along this side. So it's like we have two tables butted up against each other, and that column is picking up both of them. My children are back, and it is loud. So there are some things we probably need to think about. We need to think about live load reduction factors, because we're picking up level 2, level 3, and level 4 for live load. So what's the tributary area? Do we need to incorporate live load reduction factors? The roof, the column that's from level 4 to the roof is only picking up load from the roof, and it's picking up dead and some snow load. But the column from level 3 to level 4 is carrying whatever is on this portion of the column, because it has to get down here to the ground, and it's picking up this portion of this floor. So it is carrying dead and snow from the roof and dead and live from level 4. So just knowing what the worst case load on each floor was isn't enough anymore. We have to think about, you're very loud over there. You're very dramatic today. We have to think about what the worst case load combination is. This one's easy. It's going to be the tributary area multiplied by our worst case serviceability roof load, or our 3.33 kPa times our tributary area. But down here, the load, it's probably smart to keep dead loads, live loads, and snow loads pulled out separate, because it's not apparent to us what worst case load combination it's going to be. Because we've got dead from both level 4 and the roof, we've got live load from level 4, and we've got snow load from the roof. So look what I've done here, and I've uploaded this Excel file for you. So you can go through this and work it out on your own, and you have an example that you can do in the assignment that I've also posted the answers for. It's one that you can look at as a very reliable reference. So I recommend you try it on your own, but I don't want you to get discouraged. It's not one for any points. So I have provided the answer sheet for you already, almost as an opportunity to work through it. So you can try it, see where you went wrong, and check your answers, and then keep trying it. So I want to take some of the burden off that you need to do it right to get the marks. So I'm trying to find a balance between those two things. So you can see this is the column between the ground and level 2. So these are the loads coming in at that floor. And then you can see that it's not always going to be the same maximum load case that's going to govern the design. So look here for, oh my goodness, my children. You can see that For the column from level 4 to the roof, that's only picking up the roof, we have the worst case load is just dead and snow. It's the same as dead and snow and live, but there's no live on it. So the max is 93.2. For the column from level 3 to level 4 is picking up level 4 and the roof. We have all of the worked out load combinations here, but the worst case one is dead, live as a principal, and snow as a companion. So it seems to be the same for the rest of the way going down this column. In your assignment, you have one that is more complicated. You have one that incorporates live load reduction factor, but also incorporates having some wind cases and some seismic cases. And the goal I'm trying to prove here is that you can have different load combinations govern a column at different stories because it has different loads or values of loads acting on it. So again, you won't have to do that one for points. And you have this one here to kind of look like for a reference. And I recommend making use of Excel for that. I find it very handy. You can see that these are screen captures of Excel. So here is the column from, this is column C3, where it's got a bigger tributary area. So here's what I kind of just want to summarize for you a little bit. So let me get this standing up for you. So there are more than the standard loads. We factor the load and we reduce the capacity of the material. We combine all the factored loads to find the worst case. We combine all the unfactored loads for serviceability, and that different elements could have different worst case load combinations. So that same column running up the building had a different worst case governing load case, depending on where it was along the column. You should know how to find the soil pressure on a foundation wall. You should understand that factor of safety exists, even though it's not what we do anymore. You should understand ultimate limit states design, or the factored load combinations that I showed you, and that serviceability limit states are just the essentially unfactored versions of that, but snow and wind will have a different importance factor. And you should know how to calculate the worst ultimate limit states load case. So hopefully this lecture, being a little bit shorter after the behemoth of a lecture last week, gives you a chance to breathe. You can go through and try to replicate those load combinations if you want. Again, it's all about keeping really good tracking in Excel, I find. As I go through it, I have very complicated software that helps me, but I still like to do a quick hand check to make sure I haven't done something silly in my program, that I've entered something wrong, because a simple mistake could turn out to have very large implications. So I like to make sure I do some quick hand checks to verify those things. So that's it for this week. Now, I know you guys are stressed, and I know you guys have a lot coming up, but the next 3 weeks are pretty intense in our course. It's where the majority of what we're trying to do as structural engineers starts to come through. Some of you are going to find it very easy, because if your mind works that way, it's going to be like, oh, I get this and I've got it, and you're going to be able to move on. Some of you are going to struggle. Make use of your TAs. If you need the time, book ahead with them so that you can ask the questions you need to ask. Feel free to talk amongst your class group. I know you guys have ways of sharing and communicating information. Make use of each other. You guys shouldn't be working in isolation. I want you guys to be communicating with each other. Same goes for the assignments. I don't want you to just copy each other's answers, but I want you guys to communicate with each other. You would normally be doing that, and I don't expect you to be working in isolation just because your answers are going into a computer. Exam, I expect you to be working on your own for the exam. That's the time that you are supposed to be working on your own. But I want to make this as painless as possible for you. But I do still need to get the information to you, and The information is the information it is. I'm not being mean. It's information that's out there that all the other universities are teaching their architecture students as well. And I'm trying to make it as easy as possible to do on Quercus with not have one wrong mistake penalize you too much. So that's a thing that I've really been struggling with and trying to make it as fair as possible for you guys. Any other questions, comments, or concerns, feel free to email me and let me know what you think we could be doing better. All right, guys, talk to you next week.